Good morning, good evening. Welcome to AI Foundations. I just want to make a quick note. There will be a maintenance on the Learning Center this Friday night, Saturday morning. We will be posting the replay, but if you see some issues trying to get access to the replay, either Friday night or Saturday morning, it's just us going through maintenance. So without further ado, today we're going to get started with Module 3, Session 4, the next level of ML and ensembling and automated machine learning with Parul Pandey. So it's very exciting. I think today we'll also have a demo too. So I'll turn it over to Parul.
Thanks, Rafael, and welcome everybody to this final leg of the Introduction to Machine Learning module. We've been together for the past 2 weeks, and I hope you all have enjoyed the sessions. So let's get started with the session today. So before we go forward, as is customary, we'll just have a quick look around what we've learned in this session or in this module till now. We started with the first session with understanding what a data science problem looks like and how you can convert your business problems into data science problems. Then we went on and then we studied how the entire data science pipeline is established and how the workflow happens in the industry. Then in the last session, we went over the types of machine learning, the various algorithms, some of them, the important ones, which fall under different categories. So today we come to the last part where we will try to improve the accuracy of our model through ensembling. And then we would also study about automated machine learning, which is also touted as the next wave of machine learning. And this will be followed by an AMA session and a study group session on the weekends. So the basic idea or the basic points that we would be covering is broadly divided into two halves. The first half covers the ensembling part and the second half covers the automated machine learning part. I'm going to discuss what is ensembling, what are the basic and the advanced techniques, followed by what is automated machine learning, what are the various frameworks in the market which utilize automated machine learning, and a quick demonstration using one of the AutoML tools, that is H2O AutoML, which is an open source tool. And then we'll just wrap it up with a quick summary. So let's get started. So what is ensembling? Now, ensembling is an English word, and which means to combine different things together, that is to stack together. And what it means in machine learning is to combine different models. Now, these models could be different, they could be same, they might be using different data sets, they could even use the same data set. And why do we require ensembling in the first place? So the ultimate thing or the requirement when we create a machine learning model is we want our model to give us good predictions, correct predictions, a better accuracy. So one way of getting good accuracy is by tuning the parameters of a model and taking a good algorithm, taking more data. And another could be possible solution is to actually combine different models, which individually doesn't give good results, but when they're combined together, they give some great results. And we'll see how and why do we do that. So let's just quickly go over the definition of ensembling. So ensemble learning is one of the most effective way to build an efficient machine learning model. And you're combining the decisions from multiple models to overall improve the performance of your model. So you must have heard about some of the state-of-the-art algorithms like gradient boosting, or to be very specific, XGBoost, CatBoost, LightGBM. So all these algorithms fall under ensembling category. And if you've heard of Kaggle, so Kaggle is a data science platform where a lot of companies, they post their data science problems. And data scientists from all over the world, they compete to get and to solve those problems. And if you closely look at the solutions, it's always ensembles which win, or which clearly sets apart the other solutions. And you'll see a lot of times people resorting to techniques of XGBoost, LightGBM, CAD Boost, and so on. And so if you want to win competitions, you need to pay attention to ensembles. Okay, so we know that we can combine multiple models and the resultant model gives a great accuracy. But if you just want to wrap your head around the intuition behind it, I could give an example, a very different example, but which could actually tell you what essentially happens under the hood. So let's say you've written a blog, and once you've written a blog, you want to publish it. But you think that, before publishing it and before putting it out in front of the world, let me consult my best friend and let me ask for his or her feedback on the blog. Now, your friend is a little partial towards you and doesn't want you to feel bad. So he gives you a rating of 9 out of 10. But he doesn't really read it and doesn't really critically see what you've written, but just gives it, because of the friendship's sake. But you think maybe I should go and take a feedback from some of my colleagues at work. So then you go to 3 of your colleagues and you ask them to individually rate your blog. And so all 3 of them give different ratings and they don't know what the other has given. Now you see that here the ratings are a little different. Whereas your single friend gave you 9 out of 10, which means your blog is great. Your colleagues even gave you a 7 on 10 and even an 8 on 10. So this makes you feel that I think the feedback of the colleagues is much better than the feedback of the friend because it's more diversified. And then what you do is you go to a large gathering of people and you ask them to rate it. And they rate again, depending upon how they like the blog. Now, the responses in this third case would be most generalized and diversified because now you have people with different sets of skills. So there might be some people who are writers, but there might be others who haven't written a single sentence in their lifetime, but they evaluate what you've written. And as it turns out, this is a better approach to get honest ratings than the previous 2 cases that we saw. So now I think with these examples, you can infer that a diverse group of people are more likely to make better decisions as compared to individuals. And similar thing is true for even data science models. So a diverse set of models will give you a better result in comparison to single models. And this diversification in machine learning is achieved by a technique called ensemble learning. So this is the whole intuition behind it. And now you get an idea why ensemble works so well. So now that you've got a gist of what ensemble learning is, let us look at the various ways in which we could combine the models. So the ensembling techniques could be broadly divided into basic ensembling techniques and advanced. And both of them differ, and you could use either of them depending upon your problem or your situation and a lot of other factors. So let's begin with the basic ensembling techniques. Broadly, there are 3 main techniques which could be used: maximum voting, averaging, and weighted average. Now, all these techniques could be used for your classification problems as well as for your regression problems. And I think by now you can easily differentiate between both these kind of machine learning problems. So let's see what is maximum voting technique. This technique is mostly used for classification problems. So for instance, you have a problem where you need to classify whether an email is spam or not spam. And you're using 3 individual models. And say for one of the email, your first model classifies it as a spam. Your second model classifies the same email as not spam. And your third model again classifies that email as spam. So for a single email, 3 models have given their own predictions. Now, as the name suggests, maximum voting, you look at the maximum vote or the predictions by each model. Here is considered a vote. And the predictions which get the majority of the vote is the winner. And so finally you say that yes, the email is spam. So this is called maximum voting technique. The second technique is averaging technique. So in this method, we will take an average of predictions from all the models and then we'll use it to make our final prediction. Now again, averaging can be used for making predictions in regression problems, or if you're calculating probabilities in classification problems. So for instance, if you look at a regression problem now, say model 1 predicts 8, maybe it's some prediction, some forecast. Model 2 for the same data point predicts 7, and model 3 predicts 9. So we'll take an average of all these 3 predictions, and 8 will be your final prediction of your final model. The third technique, called weighted average technique, is just an extension of the averaging method. So here, instead of taking the normal average, you'll take a weighted average. So what happens here is you assign a weightage to the models. For instance, if you just go back to your previous example where I gave the example of a writer, if 2 of your colleagues are renowned writers, so and they have some experience in writing, you are going to give them more weightage. You'll give more weightage to their feedback. So in the same way, we assign weightages to the 3 models. Say we've given more weightage to your first model, and then second and third, and then we'll just take the weighted average. So here, the final outcome is 7.9. So if you see here, your model 1, if you had only used one model, your model 1 had predicted 8. But now after ensembling 3 models, your prediction is not 8, but 7.9. So these are the 3 ways in which you can combine different models. And these are the basic techniques. So after we've done these basic techniques and we have an idea how we combine them, it's time we move forward to the advanced techniques, which are mostly used in a lot of Kaggle competitions. So let's come to the advanced ensembling techniques. So the 3 major techniques that I'll be discussing here are stacking, bagging, and boosting techniques. And let's just go over each one of them to understand more about them. Let's start with stacking. So stacking stands for stack generalization. So stacking is an ensemble learning technique that uses predictions from multiple models. So for instance, you can see here these multiple models like KNN, decision tree, and SVM, which are known as base models. And it uses these predictions to make final predictions on the test set. Now you have to understand the word different. So the models have to be different in this case. So what you do is you take the same data set and you're going to feed them to 3 different models. Like we are seeing here, there are 3 different models, which are called base models. The predictions that you get from these 3 models are then fed as features to a new model, which is called a meta model. So here, the predictions from individual models are combined to form features, and then those features are then fed into a new model. And then you use those predictions on the test set to come out with the final predictions. And these algorithms can be any. This depends upon you which algorithm you want to take for the base models, but they have to be different. Why? Because you are using the same data set, and if you're going to use the same models, so it doesn't make any sense. So this is called stacking because you stacked different models on top of each other. How do they perform? So for instance, we have a binary classification problem, and we took some synthetic data of about 1,000 examples, and we had 20 input features. We used 5 models as our base models: logistic regression, KNN, CART, which stands for classification and regression trees, SVM, and Bayes. And this is the accuracy. And then we stacked all of them together, and you see the accuracy of the stacked model is the highest. So this was a stacking model. The next technique is called bagging, which stands for bootstrap aggregation. In the last session, we studied about decision trees and how a decision tree is very explainable and is used for making predictions for both classification and regression problems. Now, if you combine the same decision tree, it becomes a forest and is called a random forest. So what happens in a random forest is you are going to divide the data into different sets. So for instance, here you see that these are 3 different sets from the same data set. But in this case, you are going to feed them to the same algorithm, which is decision tree in this case, but it could be any, but has to be the same. And again, what you will do is you're going to train this on different subset of original data. And in the end, you are just going to average the results. So whatever predictions you get from here, you just average them, and that gives you your final prediction. So again, the most famous example of bagging is the random forest algorithm, so which simply is bagging on the decision trees. So you see here the difference between stacking and bagging. Again, these are different techniques, and you can just apply them to your problem and see which gives you a better result. The third technique is boosting. And the algorithms like CatBoost, LightGBM, and XGBoost are based on the boosting concept. Now, boosting algorithms are trained sequentially, unlike the previous one, which were trained parallelly. So each subsequent model pays most of the attention to the data points that were mispredicted by the previous one. So for instance, you start with a data set and you use a model to make predictions. Now you're going to take all the points which were misclassified or mispredicted. So that will be used as a data set this time. You'll again pass it through a model, and again you'll collect all the data sets which were again misclassified wrong. So for instance, you had a data set and you were supposed to classify it as either spam or not spam, and you had the historical data with you, and what you found that your model classifies about 80% as wrong. So you're going to take those cases which were misclassified, you'll again feed it through another model, and then again see how many cases have been misclassified, and you'll again feed it through the model till you get some reasonable results or whatever is your expectation. So the final model, so here you say you combine weak learners to create a strong learner. So the final model, which is called a strong learner, is the weighted mean of all the weak learners. So the essential concept of boosting algorithm and why it works so well is that it combines a number of weak learners, and the individual models, they would not perform well on the data set, but they work very well for some part of the data set. So you have a huge data set and there's one model which is working very nicely for one part of the data set. There's another model which is working for the other part of the data set. And so each model actually boosts the performance of the ensemble. And this is the most widely used nowadays. Sometimes people directly start with ensembles nowadays, especially for competitions. They don't even start with the individual models. So like XGBoost and LightGBM, and they also have other important features. Say, for instance, CatBoost can handle even categorical variables. There are These models can even take care of the missing values. So hence a lot of people today directly jump into the ensembles. So just to wrap everything around, I think this diagram clearly showcases the power of ensembles. So you have three classifiers here, green, red, and blue. And if you see closely, for the green classifier, you see all the classifiers, they create a decision boundary because there are three different data points, triangle, a square, and a circle. And the idea is to create a boundary which can separate all these three data points as well as possible. But for the green classifier, you see there have been some triangles which have been misclassified. Again, there have been some circles which are going in the square boundary. Then you have a red classifier which is also misclassifying. For instance, there's a black triangle and there are circles. And similarly for the blue ones. So you combine them, use them as features, you feed them to a new model, and what you get finally is an ensemble, and you see this ensemble clearly demarcates the distance between all 3 points, and all three have been correctly placed into their own subsequent boundary. So how do you use them? If you use sklearn, so there is a module called sklearn.ensemble. So this has all the methods which could be used for classification, regression, anomaly detection, and you just use them, and they have the documentation, and you can start with individual models and then use ensembles, and then you can just compare the differences. So with this, we conclude the ensembling part. And what are the different techniques of ensemble? There are simple techniques, there are some advanced techniques, but the general idea is to combine more than one model to get better accuracy, better predictions. So this concludes the first part of the session. The next part of the session now deals with automated machine learning. Researcher Feifei Li had very nicely summed up the need for AutoML, saying that artificial intelligence and machine learning is still a field with high barriers to entry that requires expertise and resources that few companies can afford on their own. And hence, there is a need for automating the process or some of the parts of a machine learning pipeline. Now, what she means is machine learning and artificial intelligence, we know they are giving us great results in a lot of sectors and has been doing considerably well. But we should also understand that it requires expertise, it requires scientists, it requires PhDs, it requires researchers. And again, it requires a lot of other resources. Now, if there is a big company, for instance, Facebook, Google, Amazon, they can easily splurge a lot of money. But what about the small establishments? They do not have the talent, they do not even have the time, but they have a machine learning problem. So democratizing AI essentially means to enable those companies also to be able to use the AI and machine learning resources and the power. And AutoML is a step in that direction. So currently, we went over the machine learning pipeline in our second session. So what are the main challenges today that we face in the AI model development? So if we start with the feature engineering part. Now, feature engineering part is one of the most important part during creation of a model. You may want to remove certain features, you might have to combine different features into some new features, and you might have to also do some encoding. But all this requires time and also requires a specific skill set, an advanced level of knowledge. Next is model building. Again, choosing which model or which algorithm to choose. How many iterations should it be made to do? And sometimes iterations runs in thousands. And you should also have the knowledge of all the algorithms so that you can decide which algorithm is best suited for which scenario. And then again, you need to create ensembles. So again, you need to decide which models to combine, which models to stack together. So this is also a time consuming and again requires a lot of advanced knowledge. And finally, the deployment part. So deployment part requires another set of skills. You also require software engineering skills. And once you deploy them, you should also be able to explain them. So responsible AI and ethical implications. So this entire process is iterative. You might have to go over again and again till you get the desired results. It might fail. And so sometimes it takes weeks and months to even put a single model into production. And it's only after you put a model into production can you actually use it to make predictions. So this is very time consuming. And is there a way in which we can automate some of the parts? Yes, we can. And that is through automated machine learning. And that is where automated machine learning comes into picture. So for instance, so automated machine learning is the process of automating the end-to-end process of applying machine learning to the real-world problems. So AutoML tends to automate the maximum number of steps. Now this is very important. So AutoML automates a lot of steps in an ML pipeline with the minimum amount of human effort, but without compromising the model's performance. And that's a very important thing to understand, that the model's performance isn't compromised. In fact, sometimes even it is better than what it is done manually. So automated machine learning, you can think of it as a standard machine learning process with the automation of some of the steps involved. So you can automate certain parts of the data preparation process. So what are the parts that you could automate? Imputation, for instance, it could impute the missing values. So a typical data set consists of a lot of missing values. So what it can do is you can automate that process. You could just make sure that, if missing values are such, so you should use this method of imputation and so on. It could also standardize. So I was at what are the steps that we can automate in a machine learning pipeline. So we could automate the data preparation process. We could also automate the model generation process. So again, we could generate various models automatically. For instance, a lot of models are generated, and then you could decide which model performs the best. So this otherwise would take a lot of time. We could automate the data preparation process. We could automate the model generation process so that a lot of models can be generated and tested, like which performs the best automatically. And then we could also decide which is the best model, because if you do it manually, we'll have to experiment with such a lot of models. But if you automate that process, that becomes very simple for a person who is a little new to this whole data science environment. And lastly, ensembles. So deciding which models to ensemble, which models to stack, blend, or bagging, or any technique that could be used. So this could also be automated. Now, what are the advantages of actually using automated machine learning? Like, you could say that things are going pretty well. It might take a longer time with the traditional process. But what is it that automated machine learning offers over the traditional machine learning? So you could think of it as this way. So automated machine learning is useful for two sets of people. So for novice data scientists and business users who have a lot of domain experience, but they have little experience with the traditional machine learning. And it is equally useful for expert data scientists too. Now, how? So if you are a novice data scientist, pretty new to the field, and you're still learning, or if you're a business user who has a lot of domain experience, but now want to utilize the power of machine learning in your business, AutoML is going to automate the basic data pre-processing, the model training, the tuning of the model, even stacking or ensembling, and would nicely give you the results. So this is pretty useful for you because you have less experience. But then what is it? How is it useful for experienced data scientists? They already know everything. For them, it frees up their valuable time so that they can put their time to good use, maybe for feature engineering, maybe for deployment. And for these repetitive tasks, they can use automated machine learning. And this is how a lot of companies today are doing it, because time is of essence, and a lot of time should be given to your feature engineering and deployment, and you need to free up the time from the normal tasks which could be automated. So having said that, let's just look at some of the frameworks which are in the market today and which utilize automated machine learning and also offer it as a service to people. So this is the part of AutoML frameworks and demo. So there are a lot of AutoML products in the market. For instance, we have Data Robot, Google's AutoML. Then there's also an AutoML part from Escalon, which is called AutoEscalon. There's an AutoML component of Keras called AutoKeras, Teapot, Amazon SageMaker. And as far as H2O is concerned, we have two AutoML products. One is Driverless AI, which is our enterprise product, which means, like, of course, you need to pay for that. Similarly, Google's AutoML is also paid, Amazon's SageMaker and Data Robot. H2O AutoML, on the other hand, is an open source library. It is freely available. It is on the GitHub. Anybody can use it. Anybody can collaborate and work on it. So H2O AutoML is part of the larger H2O3 library, which is a machine learning library similar to Escalon. So just like Escalon has machine learning algorithms, H2O also has it. And AutoML is one of the part of it which provides automated machine learning capabilities. And we're going to look a little deeper into what H2O AutoML does and how it can help you perform a task or perform a machine learning problem easier, much faster, and with a better accuracy. So just a little introduction, if you've not heard about it. It's again, just like I said, H2O AutoML is an open source, distributed, multi-core and multi-node implementations of cutting-edge ML algorithms. So it has most of the ML algorithms that you today work with. It has the implementations of all of them. It is fast, again, because it's distributed firstly, and secondly, all these core algorithms are available in high-performance Java, which makes it really fast. But then you must be wondering that if it is in Java, then you would need to know Java. No. It has APIs provided in R, Python, and Scala. And if you do not want to code, there's also a web interface called Flow. You can simply click and run, and the whole machine learning experience you can solve a problem using just the web interface. It's very easily deployable because it's in pure Java. So again, you can output the final implementation or the final model, which you get in as a Java coded object, and that you can easily deploy. So these are some of the highlighting features of H2O's AutoML. Let's actually see how it does work by taking a real example. So here's a case study that I'll be going through. So this is called predicting material back orders in inventory management using machine learning. This is a pretty real case. This happens. This is where machine learning is utilized. And the goal here is to predict whether or not a product will be put on back order status. So we are given a number of metrics of the product. like current inventory, transit time, demand forecast, and prior sales. And it's a classic binary classification problem. So you have to know whether yes or no, whether the product will be put on the back order or not. Now, why this is such an important problem or important use case of machine learning? Because material back order is a very common and a pressing supply chain problem. This impacts the inventory system and also impacts its effectiveness. So you need to identify parts with the highest chances of shortage prior to their occurrence. So you should know which product has the most probability of shortage, so that you could supply it beforehand. And this also gives an opportunity to improve the company's performance, because if you are able to gauge that this product is going to fall short, so we need to supply it before that happens. So this is a problem where machine learning is used, and we would today try and attempt it with H2 AutoML. So this means a lot of tasks like choosing algorithms will be done by our machine, and again, calculating which model performs the best will also be done by the machine. So traditionally, what we would have done is we would have taken one model, we would have evaluated it, then we would have taken another model and evaluated, and so on. So let's see how AutoML does that. So our methodology would be, it's a simple workflow like we had discussed in our previous sessions. We load the training and the test data sets. And if you don't have separate, then we're going to just split the current existing data set into two. We specify two variables, two kinds of variables. One is the response variable, the variable that we're trying to predict for. So here it would be whether the product will be put on back orders or not. So there will be one variable. And the rest of the variables are called predictor variables, which will help us to actually predict. We're going to run our AutoML specifying the stopping criterion. So for the case of H2 AutoML, we could either specify the number of models that we wanted to create, or we could specify the time for which it should run. And then it will present a pretty leaderboard with all the models, with some of the models that it has created, along with the ensembles also. And then we could just decide which model should we want to go with. So for using H2O library, you have to start a cluster. And what you do, you import H2O. And if you don't understand all the code, it's absolutely the next machine learning foundation course. But this would just give you an idea as to how things would work if you actually code. So you import the library. Next. So now you have a cluster running. So next, now what we have to do is we have to load our data set into the cluster. So here I've just given the path of the data set. So this is the GitHub link. You could just use a data set from anywhere. You could even use it from a local machine. And once you have the data path, you will just load the data into H2O. So if you see here, I've imported the data set, and I've just defined I've given the path where the data set resides. So it's very simple, you just import a file. Now let's just look at the data. So what the data has. So you see there are a lot of attributes here. You have like forecast of 3 months, forecast for 6 months, for 9 months. And you also have some lead time and sales for 6 months and 3 months. So this is what our data set looks like. It's a standard tabular data set. And this is pretty normal how we see it in any other problem. So now we have a data set into H2O. Let's start with the interesting part. So firstly, we need to split it into two sets. Again, we're going to train our data set on the first part, and then we are going to evaluate on the another part. So we split it into train and test set. We'll train it in the ratio of 80:20. 80% of our data set is the training data, and the rest 20% is our test data. Make sure, or what you have to understand is, The test data is something that is just set aside. So you cannot use it for learning or for modeling or for training purposes. Once we have defined our training and testing data sets, we are also going to define our response and predictor variables. So the response variable is the variable that we want to predict. So it is went on back order. So this is in our data set. So went on back order, and it represents whether a product went on back order or not. So this is a binary response, okay? It could either be yes or could be no. We can remove some of the columns which we think are not important here. So for instance, things like serial number, so we can just remove it. And rest of the columns which are left are the predictor variables, because we are going to use them as predictors because they're going to help us to predict. So all these columns we are going to put under X, and something that we want to predict is put under Y. So now we have Y and we also have X. And now we simply run our AutoML. We just specify the maximum runtime, that is, we want it to stop after 122 seconds. This is something that I've given. By default, it runs for 1 hour, but then you could just decide yourself. And or you could also, instead of maximum runtime, you could also specify the number of models that you want it to actually train on. So that is something the user can decide. But if you leave it, it will go by the default settings. So you don't even need to touch it. You simply say h2 AutoML and aml.train. You give your data set, training data, you give your predictor variable, and you get your response variable. And that is it. And hence your machine starts working and your AutoML sets into action. It will choose the model. It's going to test the models, evaluate the models under the hood. What final result you'll get is a leaderboard. So the leaderboard will give you the top 10 models which are built by AutoML. Now, I think you can also see that we did not choose any models. We did not specify which model the machine should use. It has used 10 models. Of course, they were in the H2O library, and it puts them on a leaderboard in the order of their accuracy or the metrics. And it gives us more than one metric. It gives us AUC, log loss, again, mean per class error, RMSE, and MSE. These are all the evaluation metrics. And the top two you see are stacked ensembles. Now, this just shows how well the ensembles work, because in the setting also, the models which performed the best were the ensembles. And then there's an XGBoost, GBM, XGBoost, GBM. So you can look at the leaderboard and you can decide which model you want to use to be put into production. Either you could use the ensembles, or if you don't want too complicated models, you could go with the other ones like XGBoost. So this is a leaderboard, and this just shows what went under the hood. And so this eliminates all that iterative process of tuning, of parameters, of deciding which model to choose, because the machine has taken the best decision for you. And it also shows how it decided that the ensembles were the best, because it highlights the metrics in the descending order. So this was a small demonstration of H2O AutoML capability. It has more features. It's very versatile, and it's an open source. You can go to the GitHub repository. You could see the tutorials and the examples, and you could also use your current problems with the AutoML and see your results. So with this, I conclude the last and the final session of the machine learning module. And let's just quickly go through what we've just understood. So we went, why do we need ensembling, and what is the advantage of ensembling? We went over the basic and the advanced techniques. Then in the second part of the session, we looked on what automated machine learning was, what are the tools in the market, and what were the different frameworks, and why AutoML is today called as the next wave of machine learning. And then we quickly saw a demonstration of an open source library called H2O's AutoML to work through a machine learning problem. So with this, I finish the machine learning module. The next session will be on introduction to deep learning, and that will be held on Tuesday, July 28th at the same time. Again, as you all know, there's a study group and an AMA group which happens on every weekend, and you could attend if you have any doubts or you have any other questions regarding the material here. Also, the quiz, you can just showcase it to the world. Thanks a lot for joining.
There's a question around showcasing resources.
So it is the H2O 3 tutorial that is on our training. So that will be given as a link in the slides. And apart from that, on a GitHub also, we have a lot of material on H2O AutoML. If you just even search, you'll get that. And it has great source of resources like tutorials, examples, and a very comprehensive documentation.
Great, thank you. And I shared some of those in the chat. Okay. So I want to thank Parul and thank everyone for joining. We will have the study session this weekend, and next week we will continue our journey here on AI Foundations with exploring deep learning, right? So we will start, I think that's module 4. And so Sayam has a very interesting set of presentations and some demos that kind of explore deep learning and how that's leveraged within AI and building AI solutions. So thank you very much and have a good day or good evening.